Okay, you can see most of the real world information is in an analog. Speed or weight or pressure, light, intensity, and position measurement are all analog in the nature. The following show a digital system with analog input, analog output. Analog input here, for example, when you're talking to your phone, the signal will be analog signal. Okay, so basically the computer cannot do anything with the analog signal. Inside the computer, only the binary, either 0 or 1, and yet nothing else. So your voice have to be converting into the binary. Okay, so that's what they call to the encoder, analog digital converter. They have to convert your voice into the binary. Then they can go into the digital processing CPU, okay, to do it. After the CPU done anything they're sending out, the data coming out will be a binary, okay? However, like, your voice go to the speaker, they have to be analog, cannot be binary. So they have to go to a decoder. That's what we call a digital to analog converter. Then they will be coming out. The analog input voltage could be produced by a transducer. Transducer is defined as a device that converted one form of energy to another. For instance, a photocell could be used as an input transducer to give a voltage proportional to a light intensity. Light energy is being converted into electrical energy by the photocell. Another transducer may include microphone, speaker, or temperature. Okay, now this is for bit D to A converter. Output waveform DA converter. At input are provided by the binary counter. You get the binary counter 4-bit. You understand 4-bit, the counter can count from 0 up to 50. Okay, input A, B, C, D. Binary. When they go into the device DA converter, digital convert to analog. Okay, this is a simple. Try to understand. Okay, D to A converter. The solution is 1 volt. Now, if you get the clock, counter will count 0 to 15. You see that 0 here? Go up to 15 and try again. Keep going. Okay. 0 to 1 volt, 2 volt, 3 volt. That resolution, step size 1 volt. Every time you changing the binary, they changing 1 volt. Okay, that's how the DA converter working. Now, this is the real one. We will be working on the lab. One very popular and inexpensive 8-bit DA converter. Okay, that is 808, and its equivalent, the MC1408, a block diagram, pin configuration, and typical application itself. Okay, the circuit to figure 15 that SC is set up to accept an 8-bit. Okay, now you can see this is the 8-bit DA converter. This is input A0, A1 up to A8. That's the input. Okay, and this is the inside. Okay, NPN current short pair. Basically, they're using the transistor inside. And this is the pin number. Okay, 1 up to 16. Okay, let's see. Okay, that's just a general. And now you can get another one, DA converter. You can see you can get 1, 2, 3, 4. Same for input. However, the output, if the input 0, output 0, and the next one will be minus 0.626, and keep going. That's a different analog voltage. Resolution of the converter is defined as the smallest change that can occur in analog output as a result of a change in digital input. Okay, resolution equals step size divide full scale times 100%. Okay, reciprocal of the number of discrete steps in the output. For instance, 4-bit DA converter had 15 discrete steps. We already talked to you. You get 4-bit, they can go in from 0 to 15. Okay, the resolution will be 1 divide 2 power 4 minus 1 times 100%. You get 6.67%. General resolution will be calculated by this formula. Okay. Resolution equal 1 over 2 power of n, depending how many bits input minus 1 times 100, where n is the number of bits. Okay. And the total number of steps. 2 power of n n minus 1. I given you example. You get only 4 bits. Okay? So basically they get a 15, 16 steps. However, total number of steps will be calculated by 2 power of n. That means 2 power of 4. 16 minus 1, 15. That means you can go from 0 to 15. Okay? Example. Determine the resolution of 8-bit and 12-bit. Now, how can we calculate? Remember, this is the formula. Resolution equal 1 over 2 power 4 minus 1. You know how to calculate it? I tell you, 1 over 2. What power?
8.
I'm talking about A.
8.
8-bit. Power of 8.
Mm.
Okay. Minus 1. Okay. Times 100. So that's why you can get the answer here. Okay. And another one. 5-bit DA converter. Produce VO equal 0.2 volt for digital input of 0001. Find the value of for a 1 input. How do we calculate that? They get a 5-bit. And basically one. Go ahead. You get a 5-bit. First thing 0, 0, 0, 0, 0. Next step will be 1. Okay. And basically they get 0.2 volt. So basically 5-bit, then you can go in from 2 power 5. What you get? Is it 32 or what? Yeah, that's 32. Minus what? 31 step. Okay. Each step will be 0.2 volt. Okay. So now when you get 1, 1, 1, 1, 1, what's the number? That will be 16. That will be 8. That will be 4, 2, 1. Okay, I think 31. And you multiply by 0.2 volt, then you get the answer. In here. Okay. A 10-bit DA converter has step size 10 millivolt. Determine the full scale output voltage and the percent resolution. We want to know how many volt. Full scale. 10 bit. 2 power of 10. One 0.24. Okay. So for calculate the output voltage, then you have to know how many steps. Two power of n minus 1. 1, 0, 23. Okay. Ten millivolt. Ten point 23 volt.
Fam, I got a question.
Yeah.
So for 10, you go 2 power 10, you get 1024. Then you minus 1, you get 1023. Then when you take the reciprocal of that and multiply it times 100, what does that give you?
Okay, let's see what formula here. Okay.
Okay, the 1023 is well, 10 is the number of steps, right?
10 will be, now if you're talking about step,
The exponent on n represent what?
okay, now get a simple one first. You get 4 bit, right?
Oh, it represents the bits. That's what it is. It's the 10 on the exponent represent the bits.
Yeah, it's represented by the bit, but you have to understand on basic here. Okay. You get a 4 bit. How many steps you get?
2 to the 4.
You understand you will be here.
Yeah, it's 16.
Now,
2 to the 4. You said 2 to the 4.
yeah, 16, but it's not step. You can count 1, 2, 3, up to how many?
15.
15. So
Yeah,
basically, the number
it's
step will be 2 power of n minus 1.
minus 1. Yeah, right.
That means how many steps you get. Okay. total number step to power of n minus 1. So if you get 10 bits, to power of 10 will be 1024. Minus 1, you get the total number of steps. Okay? And step size is 10 millivolt. Okay? So you can calculate the voltage coming out. Okay?
Okay.
Our voltage. You get the step size time 10 millivolt. Okay? So you can get 10,230 divide 1,000. You can get 10.2 volt. And if you want to calculate the resolution, okay, go into the resolution will be 1 over 2 power of 10. One over 2 power of 10 minus 1 times 100.
And when you work the whole thing out, don't you get 0.09775? No, go back to where you at, Mr. Frank.
Just a minute. That's what we're talking about resolution. Times 100. Okay. That is how to calculate the resolution.
So the 0.09775 is the resolution, right?
Okay, let's see. 2 power of 10 to 1024 minus 1.
Minus 1, 1023.
Okay, 1023. Okay, inverted. 9.77
Right.
times 100. 0.097.
Right. That's the resolution. How did you get the 10 millivolts?
They're given here.
Oh, it has a step size of 10 millivolts.
Yeah, one step.
Mm-hmm. And the where it says V out FS, what is that?
Which one?
Right there on your example.
VOFS means full scale.
Full scale equal voltage. Yeah, so what is it? What is that? What did you get?
10.23.
Oh, that's what the 10.23 is.
That means the maximum voltage you can get.
So that's the 2 to the 10, which is 1024, and then minus 1 is 1023, and the 1023 is the full scale.
Right.
Okay, thank you.
Now, this what the circuitry you have to deal with when you're working on the lab. That's a DA converter, okay? If you're looking and you can see how many input, that's a binary going from A1 to A8. 8-bit, okay? And this will be using power 12 volt. Okay, the one we're using in the lab will be plus 15 and minus 15. Okay? So basically the output will be here. You see that? Current out. Okay. Now, when the current coming out, we cannot measure the current. So they adding this circuitry. We have to add in what is the name of this circuit. Okay, this is the circuitry try to converting current to voltage.
You mean non-inverting?
Converting
I mean
current
inverting,
invert.
because it goes into the minus sign.
What you mean? Go into the minus side. They will be go the other side. This is the draw by electron current. Okay, we're using the conventional current,
Oh, okay.
so they will be opposite. Okay, so basically analog output here, Vout here. Equal I times RF. Okay. Now, when you measure the output, you will be get the voltage. Now the important here. This is the connect outside. Okay. For this DA converter, the reference current coming in maximum is 2 milliamp. Okay. And the current coming out, same thing. Maximum will be 2 milliamp. They using the current reference to get the output current. Okay. So when you apply 10 volt here, okay, if you measure at pin 14, what you think you can get?
Oh, this is the one where 14 and 15 is 0 because it's ground. And 14 is you got 10 on one side, so you can't have 10 on the other side.
My question is, if you apply 10 volt, go to the 5 kilo ohm, you measure pin 14. What do you think you can get?
You mean current?
Now I measure voltage. We
You
not
get
measure
zero at
current.
14.
Good.
At 14, you should get 0.
Who else? Okay. Why you want to get 0?
Because you cannot have 10 volts on both sides. Where the number 14 at, you can't have 10 volts there, and then on the other side, you got 10 volts equal VREF. You can't have 10 on both sides.
How come you think you get 0?
Because I can't think of the right word to say, but like in DC when you was training us in that, you can't have like the same voltage on both sides. I can't think of the right word to say, Mr. Graham.
Who can tell me? 0 is correct. But how come? You want that to be 0?
Nah, I can't think of the right word.
Saturate.
Why? How come? The thing is now you have to understand when you're working on the AD converter, you have to deal with that to make sure they're working or they're not working. I say, we measure pin 14. We want that to be 0. Why? The reason is you want how many milliamp? 2 milliamp, right?
Right.
So one side 10 volt, the other side must be round. So you divide 10 to 5K, you get 2 milliamp. If pin 14 not 0, you cannot get 2 milliamp.
So the side where pin 14 is at is act like ground, right?
Exactly.
Okay, that's what it is.
What happened is inside the DA converter, inside here, they get a circuitry connected to
Ground.
ground. That means they connect to the transistor. Okay? So transistor will be connected to ground if it's working. And then you can get the current out. And that will be maximum will be 2 milliamp. Okay? V out equal 0 to 10 volt. Okay? That's what they're telling you right here. Depending on, okay, what the binary equal. Full scale, that means all input at logic 1. Then you can get maximum will be 10 volt. Okay? However, it said V reference time A1, A2, A3, A whatever divide by the number and telling you the maximum of the voltage of this DA converter going from 0 volt to 9.96 volt. That is the way they build. We cannot do anything. Okay. This ICDA converter, block diagram, pin configuration, typical application. Okay, now. In order to measure the output, you can see they get two counter. 193, 83, 83. 4 bit, they can count up to 256 number. So how many input? 1, 2, 3, 4, 5, 6, 7, 8. Okay. In order to see the output, they connect that converting current to voltage display on oscilloscope, and you can see oscilloscope look like. That means a 0 here, they count to maximum voltage here, and they drop to 0, and they keep going. The thing is the counter will be counting 0 to 55. Then go back 0 to 55. Okay? That we're not using that one. The thing is, this is a D to A converter. And we take the output DA converter, we connect to A to D converter. So that's automatic. Don't have to using the scope. Okay? That's a very simple thing. Okay? Okay, now that is counter RAM AD converter. Now we're converting analog to digital. The one we just get through it. That means DA converter. Okay? And now we're learning idea about AD converter. That is the analog input. For example, okay? 5 volt, 6 volt, 3 volt, analog voltage. Okay? When they go in here, this is a clock oscillator. Okay? Try to get the counter. Like I said, we get 8 bit. That means you can get 255 step. Okay? Counter. That's 8 bit. So when you get the clock coming in, okay, then the counter will be counting 0, 1, 2, 3 up to 55. Okay. Now we can pick an example. I get 4 volt here. I want to see 4 volt analog converting to the binary. See what happened. First thing, this is a comparator. Okay? They compare between positive input and a negative input. Okay? If positive higher than negative, then you get logic 1. If a negative higher than positive, you get logic 0. Okay? So, at the beginning, you get input binary here on 0. And they go into 8-bit DA converter. Then look like we can get output coming here. 0 volt. Okay? In order to get a 0, you can see they have to using the switch here. Okay? They close that down. They will be clear. The counter. Okay? Clear the counter so you get on 0. On the input binary 0 go to 8-bit DA converter. That means converting to analog, you get 0 volt. So you get a 0 volt here. 4 volt. Higher than 0. So logic output here will be 1. Okay? You get a frequency coming in. Okay? And with 1, that's telling you get a clock going into here. And the counter will be start counting. Okay? And the counter will be counting. You see 8-bit DA converter here. Okay? They can count up to how many volts. However, when they count up in 4.2 volt, for example, then now one negative side higher than positive 4 volt. Output of the comparator will be go to 0. And 0 will be stop frequency coming in. Okay? That means end up conversion. Okay? If you get a 1 here, then they get frequency coming in to count it. Okay? When they get higher than 4 volt, 4.2 volt, and they get 0 here, they stop counting. So the binary in here will equivalent to 4.2 volt. Okay? And this go into flip-flop here, and they get output here. So this output will be equivalent to 4.2 volt. How that AD converter working? Depending on the solution of the AD converter, they can be 4.2 volt, they can be 4.05 volt. Okay, that means the accuracy of the AD converter. But the general AD working like that. That's just a picture, basic picture. The difference will be the resolution. That means they're asking for the difference will be 0.0001 millivolt. So they can get exactly almost what analog voltage should be. Any question on that? Let's just try to understand that is a basic for A to D converter. When you're working on the lab, you have to using both one D to A converter, connect that output to the A to D converter. Okay, so you don't have to using manual. Computer will be verified. ADC. This is the IC, analog digital converter. If you're looking on that one, how many pins? 20 pins. And they're using VCC. That means they're using 5 volt in digital system. Okay? And they can telling you what will be input, what will be output. Okay? When we get the lab, we will go in detail on that. AD converter. That means if you're doing by hand, you can connect this input to variable resistor, okay, and connect like exactly like they're doing here. Okay, you close the switch, you can get a binary coming out. However, what I'm saying is, we're working with the computer. So you can get the input analog coming in, and they coming out will be binary. And binary, the computer will be take care of that. That's it. Any question? Anything? Make sure today will be the last day on the Zoom 2024. Okay. Next week, you guys don't have a class Zoom on Friday. Take one, get one on Thursday, but not you. And you can get a vacation up until January 5th, 2025.
Sounds good. Thank you, Mr. Penn.
Okay, so basically, I wish all of you guys get a very happy holiday. Okay, Merry Christmas to everyone.
Same to you. Thank you.
You too, sir.
And you, Mr. Pham, eat a turkey leg.
Thank you.
Merry Christmas.
I will meet you guys on this Monday coming only, and after that, up until 2025.
Okay, see you Monday.
See you next
Yeah.
year.
Okay, happy everyone. Okay,
Thank you.
good night.
Good night.
Good night, sir.
Good
Take care.
night.